Hello everyone. Today I'd like to present general relativity as a direct perception. So it's a little bit, I wanted to use the analogy of you want to go to a new city like let's say Florence, Italy, and typically the first days out you want to walk the main streets and look at some of the special shops and maybe the museums and get a good ground level view and with a lot of sort of picking up little details which are of interest to understanding the terrain and getting a feel for the new city. And then at some point, typically, you crave to have a view from on height. So like in Paris, you go up the Eiffel Tower. And Florence, I remember we actually did this. We went up this tall church, had a dome on it, and they had enough space there you could crawl up, and get to a lookout that they had there and look down on the entire town of, in this case, Florence. So you get the top-down view, and then you can see well, not every last detail from the ground level, but you get to see all the pieces in their relation to each other all at once from a top-down view. Well, that's what this presentation is. I want to put everything together in a concise, accurate, and actually rigorous and complete view, so you can really see as a direct perception the whole thing. So let's begin. So here I'm showing what we are going to derive, which is right at the middle of this page, equation number 96. And it's Einstein's gravitational field equation from a book that he wrote himself. I always like to go back to the source for these things because he struggled for years. He knows kind of some of the pitfalls to avoid and a lot of the mistakes to avoid. So I like to go back to him. Meaning of Relativity, Albert Einstein. And I forgot to mention, but it's okay. We'll go to it now. That I have a link. You see the red arrow there too. It says note, free download of The Meaning of Relativity by Albert Einstein at the link below. So you can just go to that link and download for yourself the same book I just showed you, and look at that and see the equations that every now and then I bring up. And also you might want to read it yourself after this because it'll make a lot more sense after viewing this. By the way, this derivation that I'm doing is my own. I've never seen anyone start from the beginning and go right through and derive everything in very simple form. Actually, earlier this week, as often happens, there's that visual processing part of your brain, and you get these sort of images that rise up, and I saw this particular possibility of a derivation, and my response was, what? You've got to be kidding. Can it be really that simple? And I went through this, I've recorded it here, and it seems to be very simple, concise, complete, and rigorous. So it's kind of an amazing thing. I'm really looking forward to presenting this. Also, I have the links here, 1, 2, 3, 4, and this is presentation 5, so I can't put that yet. But this is for my website. On my website, Hacking the Human Time Machine, I have these 4 introductory presentations where it's like, that part where you're going through the villages and looking down the main streets and going to the shops. And this gets you very familiar at a ground level with the topic. So we go back to where I was before. Reminder that we're going to derive that expression. Equation 96, if you download that book, you can look up for yourself. And here's a note. The reference I'm using is the Albert Einstein's 1954 edition. He went through 5 revisions, which really, I want to also mention in physics, nothing is the last word. And Einstein himself wasn't really completely satisfied with this theory in total. And as he learned more, he had to do revisions, and I find the same thing. You learn more, and you sometimes even find out, oh, I'm up by 2 here, or some other thing. You got to go back wherever you want to go back and upgrade it, and that's the sort of thing that he did. This is the 1954 version. The reason I chose that is because he died in 1955, so this is his latest and greatest view. If he wanted to change anything, he would have done it before this, and it would be recorded in this. So I really think when you're going to innovate on a subject, you want to really show that you understand what the people before have accomplished. Understand it completely, accurately, rigorously, and have a really good feel for it before you sort of like have the privilege really of at least credibly innovating and maybe extending the scope of the work. So that was my goal, is to establish fidelity in my understanding of Einstein's work, so I can appreciate it fully. And then if I make any revisions thereof, at least they're more justifiable than if I just wing it, have some more errors in there, not really understand Einstein's original works. So here I also want to talk, as part of maintaining fidelity with Einstein, you have to understand, or at least I did, what he was actually saying, and what his particular choices of certain conventions are. And here, in equation 91a in the middle, the one where the red arrow pointing to it, let's see what he says. He says, we shall call this the first approximation to the GU field. He says, in considering approximations, it is also useful, as in the special theory of relativity, to use an imaginary x-coordinate, as then the GUV to the first approximation assumes the values, and he does -1, -1, -1, -1. So, the GUV is kind of a scary thing, because mostly because he doesn't really define it. It actually has some summations in there. Einstein has implicit summations. And don't worry about that, because I'm just going to write the whole thing out for this particular form. And so you don't have to worry about it with the notation, because I'm going to show you everything. And like whatever it is that. I'll do that in the next page. But I want to just show you, we established early on in the previous presentations, by measuring the inductance and capacitance of free space, that any waves within the vacuum, like in the vacuum, not riding on it or anything, intrinsic, not extrinsic. Anyway, they must travel the same distance in time as in space. In other words, they're actually two-dimensional motion. It goes in time and it goes in space, and that establishes. They call that the tensor character, and I've never liked that name. It's not tense. It's wonderful, and it's also not so complicated if you just understand, the dynamics. Anyhow, so what if you look, since it goes the same distance in I want to put another one on top here. Don't just bear with me. T squared. Yeah, no, I actually don't. This is good. T squared, the way that the distances actually add, you know this from Pythagoras, that you have to square the amounts to get the right angle triangles to add, to get the total distance of the diagonal. You go up and then you go over. Well, the distance of the diagonal, you have to take the square and then take the square root of it. And these numbers, -1, -1, -1, -1, and 91a, arise from this thinking. So it works out that the time distance in time is equal to the sum of the squared is equal to the sum of the squares of the distances. That's really what the basic waves through the vacuum, they obey this expression. And so you can, when you want to equate it to something that's never changes, well, zero is pretty unchanging and fundamental. So people like Einstein like to throw the t squared over on the other side of the equation. It becomes negative. And you have 0 is equal to x1 squared plus x squared 2 squared. You know, it might be, you know, x direction, y direction, z direction, time direction, all squared. And the time has a negative in front of it. Oh, did I say that twice? Twice. Yes, I did. So I'll just leave it in there. Say it twice for emphasis. Anyway, so as part of this choice, he says, well, I'm gonna buckle under and go with Minkowski, his professor, who suggested that let's x4 equal to ICT, and I say use c equals 1, so I'm gonna drop that out. And all my previous presentations, I left the c in there because it makes it harder, and you're tripping up when you have to change it, you know, which I did, and it keeps you on your toes. But now at this last one, I want to really move through this, and so x4 is, he says, let x4 equals ICT, but in balanced units, the c, the distance and the time are the same in balanced units. So the c, the velocity of light, or any other wave through the vacuum, equals 1. So you can just let it, you know, you don't have to show 1 in an expression. So we have then x4 is equal to ICT. So then x4 squared is equal to negative t squared. And we had t squared, and then in this one, 0 is equal to, you know, x1 squared, x2 squared plus x3 squared minus t squared. Well, x4, when you put x4 in there, you get a minus a t squared. And so, and the x4 squared has no minus on it. So you get to just stick that in here, and you get the expression 0 is equal to x1 squared plus x2 squared plus x3 squared plus x4 squared. No, Einstein wasn't happy with that either. So he, you know, it's a fact that if you multiply 0 by -1, it's still 0. 0 times -1 is still 0. So another possibility is to multiply 0 by -1, and the other side of the expression as well. And you know, negative x squared plus the minus negative x2 squared minus negative x3 squared minus x4 squared is equal to 0. So that's the one that Einstein chose, and you get negative, 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 negative. And because I want to maintain fidelity with Einstein, I'm going to choose that as well. Okay, so, and then here he says these values may be collected in the relation. He says g of v, that's that expression, a function, is equal to negative, and this is the what they call the Dirac delta function. Again, it's to kind of scare you off. It's, which is, anyway, Dirac delta function is one of the stupidest functions I know. It's basically has only this purpose. When the indices are the same, like u and v, when u and v are the same, this thing is equal to 1. When u and v, I'll say it again, when u and v are the same, the Dirac delta function is equal to 1. When u and v are not the same thing, like any of the other possibilities, when we're indexing them 1, 2, 3, 4, you know, that's what u and v are. So, you know, and there's an implicit summation in there, because it's going like, you know, in your car, you do the odometer, which all of us, I think, you know, if somebody says you pull your car in to have maintenance done on it, and they'll say, what's the mileage? Well, you go out, you read the odometer, and it's like so many bits of a mile, so many miles, so many tens of miles, so many hundreds of miles, if I remember correctly. That's more, the odometer is more complicated than this thing. So anyhow, so this thing goes through the same thing. It has the sum of v goes 1, 2, 3, 4, and u stays at 1, and then u goes from 1 to 2, and then it's 1, 2, 3, 4, and then the v, and then u goes to 3, and then v goes 1, 2, 3, 4, and u goes to 4, 1, 2, 3, 4. So there's 16 of these things, implicit. One of the things that kind of bugs me about Einstein is he put his expressions don't overtly show what's going on inside, but I'm going to always do that for you guys, so you'll see as part of being able to see everything all at once is to make it explicit. And I started here, but you can see it gets. I have to go dot dot dot. I don't want to do that. So I also, but before I switch pages and show the full thing, I just want to make a comment about what this why g of v goes to the Dirac delta function. That's a very simple thing. Is because in this assumption, considering approximations, that's what Einstein's talking about now, considering approximations. Now he's using the, I call it the pseudo-flat space approximation, which applies to, for example, our solar system. And most of the masses that you encounter are small enough that they actually don't bend space very much. For example, if you calculate it, the amount that the Earth bends space at its surface, which is the highest gravity we can get, the curvature, if you look at the radius, you know, if you have a curve, there's a radius of arc. That radius is like 2/3 from the Earth to the Sun, that long. So it's that arc is pretty darn straight. So it's straight enough that you can use this approximation where you say, oh, let's just ignore the differences and say that space is flat. Now, when space is flat, all the 4 dimensions are orthogonal to each other locally, and that orthogonality ensures that they do not infringe on each other. So if you take the change in y with the change in x of the actual coordinates, it's equal to 0. And the change in y with the change in z, etc., is equal to 0, and t is equal to 0, because they're independent when space is flat, or in this case, is close enough to be flat, considered flat. But if you say, what's the change in the x dimension with the change in the x dimension? It's 1, right? What's the change in the y dimension with the change in the y dimension? It's equal to 1. What's the change in the z dimension? Change in z, it's equal to 1. And change in the time direction with the change in time is 1. So those are those lines down there. But remember, Einstein chose where you multiply 0 by -1, you get negative, negative, negative down there. Anyway, same deal. It's really so simple once you see it. And I'm going to write it all out next. Okay, so I'm going to move myself over a little bit. I'm going to do that every now and then. There we go. So where space-time is effectively flat, and thus the coordinates are orthogonal, then g with the subscript uv, that means the derivatives have a certain form, times g with the superscript uv is equal to 4. And it's like, wow, it's equal to 4. Now 4, we're talking about 4, just the number 4, nothing special. Remember 2 plus 2 equals 4? Well, we're talking about that 4, okay? And we can call that number a scalar because there's no direction. It's just a number. Like I should talk about scalars. Like your temperature. It's a number, and what is it? 98.6 degrees Fahrenheit. That is a number. There's no direction in the normal use of it. And if you have like 1 apple and 2 apples and 3 apples, well, you got 3 apples. It's a number, and we have very good intuition with that. So when I talk about scalars, we can use our intuition accurately. When we talk about what they call the tensors with the 2 directions involved, we don't often think about, although we do it in stress, and I always love stress. So I kind of, and stress is in your, you know, when you stand up, you have stress on your knees. So it can be highly intuitive, but for most of us, including me, until now, it wasn't, my intuition wasn't totally trustworthy. So we have to differentiate between scalar, which is just a number, and the tensor, which has two directions that you have to keep track of sometimes in the calculations and derivations. And we do that here, you'll see. Anyway, we have the subscripts. When you have subscripts on the GUV and then superscripts and you multiply them, the derivatives in there, which are just basically velocities. The GUV has the derivative in one form, let's say meters per second or something, and the G with the superscript has, instead of meters per second, we'll have seconds per meters. It's the inverse. So these are inverse functions, and there's summation. So the inverse is when you have A over B and you multiply it by B over A, the inverse. The B's cancel and the A's cancel, you get 1. And this is a sum, and it worked. I'll show you below. So let's see, blah, blah, blah. Yeah, you know that when flat space, and that's what we're talking about to illustrate this, the GUVs become the direct delta function. So I'm going to go through, and I'm going to, remember I was talking about how it's like an odometer, and one wheel goes through, and then the other one upgrades from 1 to 2, and then the wheels go, and it goes from the next one before, it goes from 2 to 3, and blah, blah, blah. Well, I show you what this G UV times G superscript UV in this nearly flat space in terms of delta functions actually says. Notice it's in this one line there. It says negative DUV delta UV times negative delta UV with subscripts and superscripts. Well, the negative times negative, that cancels, so there's no negative in it anymore. And see this expression here, I start with the green one, which is direct delta function 1, 1 times direct delta function 1, 1. Now, the whole friggin' purpose of the direct delta function is that when the indices are the same, it's equal to 1. So this first term here is 1 times 1. Then the next one's 1, 2. Remember the first wheel's turning like an odometer. So 1, 2 times direct delta function 1, 2 with a superscript, and then plus 1, 3 times, you know, blah blah blah. Those are all different. You notice that the superscripts and the subscripts are different, and the only purpose of a direct delta function is when they're different, it's equal to 0. And that's because, like I said, the coordinates are independent of each other. Those cross terms, where you're like dx, dy, are 0, because they're independent, except, you know, dx, dx, which is 1. So then we continue on, and the wheel changes to the second wheel changes from 1 to a 2, and the next one. So you have plus 2, 1. And then and times 2, 1. The first term 0. Then the second term delta 2, 2 times delta 2, 2 subscript superscript. Bingo! It's like 1 times 1 again, so you get 1, right? Then the next one, delta, the second wheel turns from a 2 to a 3, and the first wheel goes through its permutations 1 to 4 again, and you get 3 1s, you know, delta 3 1s, and then you get the delta 3 2s, and then the third one in, delta 3 3 times delta 3 3. Bingo! It's 1 times 1 equals 1. And then we get to the last one, delta 4 1, the second wheel in goes from 3 to 4, and then you go through the permutations of the first wheel again, just like an odometer in your car. Delta 4 1 times delta 4 1, delta 4 2, delta 4 3, delta 4 3. None of those are the same. So the subscripts, so the delta function makes them all 0 for sure. Then you got delta 4 4 times delta 4 4. Oh, the subscripts are the same again. Bingo! It's equal to 1. So we get what I have it record that below in the next line. 1, 0, 0, 0 plus 1, 0, 1, 0, 0, 0 plus 0, 0, 1 plus 0 plus 0, 0, 0, 1, and that's equal to 4. Now this turns out I'm doing this because it's actually the most magnificent thing. To be able to see Einstein's gravitational field equation clearly and completely and rigorously, you have to understand the number 4 and the fact that it's identical in flat space to GUV times GUV with the GUV subscript times GUV superscript. That is equal to 4. So when you see the number 4, you know you can substitute G subscript UV times G superscript UV. You can, let me say that again. If you see the number 4 in any part of your derivation, you can substitute G subscript UV times G superscript UV. That's kind of amazing but true. Now, it gets better than that. This result can be generalized to any two metric tensors, G subscript UV times G UV. So even though I've derived it completely for this approximation, the field expression we derive will use using this will apply generally. So we're going to actually be able to, and this is derivation that I'm going to show you, prove it completely, simply, clearly, and rigorously, and it'll apply across the board. So this, you'll actually get a general field equation for gravity. So amazing. So often, you know, when it comes to understanding an expression or trying to derive something, you can flounder around for a long time if you don't really have a clear understanding of it, exactly what you're going to be trying to do with this expression. And I suffered from this because Einstein doesn't tell you exactly what he's trying to do, what he's trying to accomplish in his expression. By the way, I'm not knocking Einstein. He was the first one through this thing, and the fact that he could, first of all, conceive of it and then stay with it all those years where he said he felt like he was floundering around in the dark. Well, one of the reasons I think he's floundering around is he didn't understand total. Well, I don't want to talk about him because it sounds like I'm criticizing, so I'm really talking about myself. Didn't understand exactly what the equation was trying to accomplish. So let me talk about that here. I'm going to try to put it concisely in a precise paragraph here. So let me just read it. Einstein's equation, the gravitational field equation, and I'm calling it a ledger. Like an accounting ledger where you have, the purpose of the ledger is to provide you the format where you can put the credits and the debits and list them. And you need to have enough spaces for the different types of credits and enough spaces in this form, this ledger, for all the different types of debits. So you got all the credits on one side, room for all the debits. Doesn't mean that every slot you put in there for all the types of debits, they're not always going to apply in every situation. You might have no debits. You might have one. You might have lots of them. You might fill every form, every slot. But if each slot, if you got all the slots there, then you can never exceed those number of slots. So, like an accounting ledger, this is Einstein's ledger, his gravitational field equation. It is like doing providing the form with which you can do a space-time energy and curvature reconciliation. like an accounting reconciliation. So you got all the possible slots to record all the possible, like in this case, momentum densities, because they can point in different directions. So you want to record that, have a slot for it on one side. So on one side of the expression, in this case, let's say it's the right-hand side, you're going to put each individual type of momentum density, which direction it's pointing. And on the other side, which in the case on the left-hand side, I'll know it reverses it when anyway, the left-hand side, you're going to put all the possible types of curvatures. And if you were to take the right-hand side and move it over to the left-hand side, they would equal to 0. They have to balance. And like any good accounting book, you want it to balance to 0 so that you can do your reconciliation, and it would hold up to any audit that you do later because you did it correctly. So that's what Einstein's form. So let me just read what I said. Einstein's ledger is designed to record each of the 16 possible types of momentum inputs on the right-hand side, which reverses it on my screen. And on the left-hand side, corresponding to each of the 16 momentum inputs, in a 1-to-1 mapping are each of the possible types of curvatures. So you put all the types of momentum directions, densities, momentum density directions on one side. And on the other side, you have all the types of curvatures, of which there are 16 possibilities. The total sum of the momentum inputs and the curvatures must equal 0 as in any good accounting system. So I bet you didn't know that Einstein was basically an accountant. Well, live and learn. So again, we're trying to maintain fidelity with Einstein's latest published views on the subject as revived in 1954. So let's get into it further. So Einstein in his book, he says, we've got to start with Newton because Newton is correct within its scope. And its scope was, we're going to use mass as the detector in a low gravitational field like the Earth. And we're going to drop it, and it's going to go a negligible distance in space. But let's say you drop it 1 second, that's 300 million meters that it goes through time. So it's basically our detector, Newton's detector. Using mass, you pick up easily the curvature along the time direction. And I make another note. We're going to, in this presentation, use balanced units to reflect the reality that c equals 1 and balanced units. So I'm not going to have to put c in all my equations. I want to be clear, the clearest here. So unlike all my ones before, I'm using c equals 1 and I'm not expressing c explicitly here. So let's go to the first expression 1. By the way, I have these expressions numbered on each page just so I can talk to them and you'll be able to follow more easily. And we start with Newton's gravitational expression, which we probably all remember as force. I like to add force equals mass times acceleration. That's also Newton. And that's equal to gravitational constant times m1, it's the small mass in this case, times m2, like the mass in the Earth, divided by the radius from wherever you're doing the measurement to the center of mass of the Earth. And on the surface, that radius would be the radius of the Earth. Okay, so we get in number 1 expression there, force equals mass times acceleration equals m1 m2 times g divided by r squared. Now notice I put the m1 in this kind of irritating minty green color, and I did that because you can see then that it's on both sides of the expression when you're talking acceleration, so you can cancel it. Boom, it's history. So you get equation number 2 there. Acceleration is equal to the gravitational mass there, the big one like Earth, times g divided by r squared. So now that's the acceleration at one point. And if you want to talk about something that really looks at kind of like the totality of the acceleration, one of the ways to do that is multiply both sides of this expression, 2, by the surface area at the radius r, wherever you are. Wherever you are. But at the radius at which you're talking about specifically. So that might be the radius of the Earth if you're talking about the acceleration at the surface of the Earth. So we do that. We make that multiplication. And we get to on both sides by the surface area, which you should know, or maybe I'll tell you, it's 4 pi r squared is the surface of a sphere. So we multiply both sides and we get expression number 3. And we see 4 pi r squared a is equal to 4 pi r squared m2g divided by r squared. Now notice I put the r squared now on the right hand side is that irritating green color, which means it can be cancelled. So we cancel that. It's history. And we're going to move to expression number 4, but we're going to do one more thing at the same time. We're going to divide both sides by the volume at radius r, which I signify as v sub r, is the volume at that particular radius. Okay. So we have 4 pi r squared times the acceleration. This is an expression 4. Divided by v sub r is equal to 4 pi m2 divided by v sub r times g. Now we make something, another, you see there, let rho, and I had made it in blue so you can sticks out. Let rho be the mass density m2 divided by v sub r. So the mass density is equal to rho. Keep that in mind, and I make it in blue there. So for the next few expressions, I'm going to just look at the left-hand side. We're going to work on that side only, if you don't mind. So just keep that in mind. So we expand the left-hand side, and what it was 4 pi r squared a divided by v sub r. And we're going to expand v sub r. So you get 4 pi r squared times the acceleration divided by 4 pi r cubed divided by 3, which is actually the area of a sphere is 4 pi r cubed divided by 3. So I just expanded that on the denominator and left the numerator the same. However, see the r squared on the top and the r cubed on the bottom? And also see 4 pi on the top and 4 pi on the bottom. Those two things cancel. And the left-hand side of the equation from 5 becomes the left-hand side of the equation as represented in 6, which is equal to, now, with all those cancellations, by the way, you can screen save this and then go through it yourself and check. 6, 3a divided by r is the left-hand side now. And if you go through the units, and remember, c is equal to 1, so you're not going to see seconds. You're going to see unbalanced units. So I'm going to express seconds as meters as well. And the units then become meters divided by meters squared. That was the acceleration. You previously might see meters per second squared. But there's meters now. Everything's meters, including time. Divided by meters, the units are 1 over meters squared. So this is a curvature. That's the units of curvature. So that's the units of curvature. So now it's expression 7. Just looking at this. Expression 7 takes us back to expression number 4, where I'm going to, the left-hand side, we operated on it without changing it, and it's equal to 3a divided by r. But in expression 4, the left side was equal to 4 pi m2 over v sub r, which is rho, g. So now in expression number 7, I'm putting that in, 4 pi rho, which is m2 over v sub r, times g. So I've just said, I've really basically expressed expression number 4 is the same as expression number 7, but I've done some cancellations on it. So we're looking at this thing, number 7. We can divide both sides by rho, the mass density. So I do that, and we get expression number 8. 3 times the acceleration divided by mass density and divided by the radius, and you see them both in the bracket there, and in the denominator, is equal to 4 pi g. So 4 pi g. Now remember, 3a divided by the radius is curvature. So, and then we have got this now in expression 8. We've got the mass density on the bottom. So this is the curvature divided by the mass density. Let me say that again. 3a divided by r is the curvature. And in expression 8, we have 3a divided by r, and then divided by the mass density. So this is the curvature divided by the mass density. And we have, it's equal to 4 pi g, because we divided it by both sides by rho. Just, like I said, do a screen save and look at it. You'll if you don't see it immediately, you'll certainly see this. So we have that the curvature divided by the mass density is equal to 4 pi g. And this is for curvature in the time dimension only, because we're talking about Newton's approach, using mass as the detector in a low gravitational field. So, which is what Newton did, exclusively what Newton did. So I say here in the yellow box at the bottom, trying to summarize it. For curvature along the time direction, 3a divided by r divided by rho is equal to 4 pi g, and that's equal to the curvature divided by the mass density. Now, 4 pi g, 4 is a constant, although it's an amazing constant. 4, remember we just talked about the number 4. Anyway, 4 pi is a constant, and g is a constant. So that constant is equal to the curvature divided by the mass density. So we have the relationship between the curvature and the mass density. That's amazing. We just, 4 pi g in Newton's world, using mass as a detector, gives you the relationship between the curvature that you're going to detect using that mass divided by the mass density of that mass. So that's amazing. And also we have directly from 8, if you just isolate a on the one side, like divide the other side by 3 and multiply by r divided by inverse the r over 3. Anyway, you work that out. It's right there in 8, expression 8. When you isolate a onto one side by dividing by 3 and multiplying by rho r, both sides, you get a is equal to r divided by 3 times the curvature. So we have, you see, one of my first charts I did in this whole series, I suggested a very strong relationship between the acceleration and the curvature. Well, here you see that the acceleration, according to Newton here, is r divided by 3 times the curvature. Now, if r, for example, was the radius of the Earth, say you just want to restrict yourself to that, then r over r becomes then a constant under those circumstances, and 3 is a number. So basically, a then has a sort of like a constant of proportionality, r over 3 times the curvature. And so it's perilously close to saying that, you know, the acceleration is equal to the curvature in these, with this constant of proportionality. Now we know that r can vary all over the place, so it's not exactly right. But you know, when your eye and you see a curve on a diagram, space and time, and you say, oh, space-time curvature, that's It's always associated with acceleration. Well, there you go. That's why. And you got to trust your eyes, trust your senses, in the sense that you get these are physical experiments you're doing. Same way that Einstein trusted an elevator when he said, look, inside this elevator, I can't tell if it's a rocket producing that acceleration, in which case that's giving me my acceleration of gravity that I could think is gravity, but I can't distinguish between a rocket accelerating and gravity. And then he said, oh, that means that if I can't tell the difference, that gravity is equal to acceleration. That's what he called, what is this, equivalence principle. So he trusted his senses, and we got to trust our senses in a similar way. You got to be very precise and accurate, not to misinterpret even your senses. All right. So as we derive for curvature in the time direction, 4 pi g is equal to the curvature divided by the mass density, and the units are meters per kilogram. So curvature is equal, and that's 4 pi g is equal to curvature divided by mass density, and that means that curvature is equal to 4 pi g times the mass density. So if you had the mass density, for example, you can multiply by 4 pi g and you get the curvature. So this provides the translation you need for the cosmic accounting or gravitational accounting system, this ledger. If you have the mass density on one side and you multiply by 4 pi g, then you get the curvature. Now, this curvature you're going to get, we're talking right now because we're human beings and we're very good with most of our intuition is very good when it comes to scalars like temperature, number of apples, just number of things. Yeah, we have good intuition with this. So if you have a mass density and you consider it as a scalar thing, you're not going to look at the distance like what's the mass, and you multiply by 4 pi g, you're going to get the scalar curvature. We know that. Our intuition is good as long as we're talking scalars, which are just numbers without directions. But when you get into these vacuum fluctuations where it's going two directions at the same time, and this for vacuum fluctuations, same amount of distance in space as in time, and they call that, to kind of scarily, they call it a tensor, as a tensor nature. Our intuitions are not quite so finely honed, and from that comes some of the sort of surprising paradoxes that we're going to discover here, because we're going to get a beautiful, concise and rigorous and simple and clear derivation of Einstein's expression coming up. So let's go into that. But remember that the scale, if you have scalar mass density and you multiply by 4 pi g, you're going to get the scalar curvature. So let's have a look here. What do we got? Oh, wow. This what you see, these steps number 1 through 8. This is the entire derivation, starting from what we already know physically and ending in 8, where we have derived the form in detail of Einstein's gravitational field expression. So let's look at this thing. I say here, measuring the capacitance of the vacuum and the inductance of the vacuum shows that waves of the vacuum must travel the same distance in space as in time. And for balanced units, 1 second in time is equal to 300 million meters in space. So a light wave, for example, goes 300 million meters in time for when it goes 300 million meters in distance. And it's going in two directions. So one of the genius aspects of genius or genius at work of Einstein is to look at that and say, okay, waves through the vacuum have to go in two different directions or through the vacuum. And in each one of in the vacuum is four-dimensional, so each of those directions have 4 degrees of freedom. They can go, x1, x2, x3, x4 directions, and that's one direction. The other direction can go x1, x2, x3, x4. So it comes back to the fact that there's 4 degrees of freedom times 4 degrees of freedom. That's 16 possibilities. And remember, Einstein's field expression is purpose is to provide an accounting type ledger where you have slots for each of the possibilities, whether they're occupied or not. You have to the ledger scope be broad enough to capture everything and provide the relationships for each of those in a one-to-one mapping between momentum density and curvature. So the 16 possible two-directional vacuum waves then become, here are the possibilities. The mass density 1, 1, pointed in the one time direction and traveling in the time direction. 1, 2, 1, 3, 1, 4, 2, 1, and then the second wheel turns again like an odometer. 2, 1, 2, 2, 2, 3, 2, 4. And then the second wheel goes from 2 to 3, and you got 3, 1, 3, 2, 3, 3, 3, 4. And then that second wheel goes to from 3 to 4, and then you got the first wheel spinning through again, 4, 1, 4, 2, 4, 3, 4, 4. So I just went through. I explicitly expressed the fact that there's implicit summations, but I made it explicit here. And so if you just express it as a general sense, you call that P subscript UV to describe all those 16 options. P subscript UV. So let's look at the first statement here. I think it's necessary to start with something you know for sure that is physically true. Okay? That's physically true because we're making a physical theory. We're not doing like a mathematical system where you can postulate almost anything and then just work through the ramifications of those postulates. I don't like to work that way because I think physics is not. It's the mathematics has to match the physics, not the other way around. So we do that. So I asked, what has to be definitely true by the physical meaning of K? Well, K is the curvature divided by the mass density. And that means that if you take K and multiply by the scalar version, just the amount, which Newton did. And to make sure we understand it's scalar, I put 2 vertical bars in front of it. And that just means that we're doing the scalar value of the mass. And we know from the meaning of K, which is the curvature divided by the mass density, when you multiply by the mass density, the scalar version of the mass density, you get the scalar curvature. That's what it means. So we already did that with Newton's expression when we derived it. So we know that the curvature, the scalar curvature, is equal to K times the scalar mass density. That is a fact that we already know. So I write in expression number 2 there. I put it into a accepted standard notion for expressing 1. And so I'm just getting the notation correct. The scalar curvature is called R. R without the UV subscripts. It's a scalar value. And we know from the definition of K that we've been working for, which for Newton was 4 pi g, that K, except in Einstein's expression, we're not sure about K. We have to derive its value because we're using tensors and things, and that can change things. So So we're going to derive k, not in these 8, later in the next page. But through the definition of k, which is the scalar curvature divided by the scalar mass density, we know that when you multiply by the scalar mass density, you're going to get the scalar curvature. And using standard notation, the scalar curvature is called r without subscripts or superscripts. And the scalar mass densities, all 16 of them, if there are 16 slots, 16 possibilities for mass density, is T without the subscripts or superscripts. That's the scalar mass density. And we know that R is equal to KT, just from the definition that we've been working with, we derive for K, or any version of K, like for Newton, it's 4 pi G. So we know 2 has to be true. Now, we operate on 2 arithmetically. Now, once you start with something that's physically true, we know that physical reality generally follows arithmetic truth as well. Conservation of energy, conservation of charge, things like that. It obeys arithmetic rules. So we can say that R minus 2R is equal to minus KT. R is equal to KT. So R minus 2R is equal to minus R. And if R is equal to KT, then minus R darn well has to equal minus KT. So that's all I've said in 3. So we're almost through this thing, and it's amazing. It's all trite even. Trite. Now we look at, here we do something extremely interesting. R is the scalar curvature. That's actually, if we've already, I think, established earlier that, and I'm going to talk about a little bit here, just in case we didn't. R is the scalar curvature. If you multiply R by, if you start with RUV, okay, which is the tensor version, and you multiply by GUV, the derivatives of UV are inverse of the derivatives of RUV, and they cancel. So it means that R is equal to GUV times R subscript UV. G superscript UV times R subscript UV. The differentials cancel out, and you end up with R. So I can start with 3 and say I'm going to make an expression 4, which is equivalent to 3, but looks a little different. And so I did that for the first R. Now the second R, minus 2R. I take that R and I say that one's also equal to G superscript UV times R subscript UV. Because again, they cancel out. You get R just like in expression 3 when you do that to expression 4. So that's so far so good. And then I do the same thing for KT. We know that if you multiply T subscript UV by G superscript UV, the differentials cancel out, and it becomes a scalar. So for that scalar T in equation 3, I can insert this the scalar T expressed as G superscript UV times T subscript UV. So why did I do that? Well, this is one of the few sort of aha amazing moments here. Well, notice that we've got GUV times GUV times G on the right hand, on the left hand side, and the right hand side we've got GUV. All the terms have GUV in front of them, which means you can divide by GUV on both sides and take it out of there. So I take expression 4, which we know is true because we've started with something that's physically true, and arithmetically we've come to discover that 4 is true and physically true. Now we divide both sides by GUV and we get 5, which is it's suddenly we've transformed from the scalar world into the tensor world. It's like, oh my God, this is amazing, right? But here we are. In 5, we've got the tensor equation. RUV minus, now, 2 times 2 equals 4, which means that 4 divided by 2 equals 2. I know that's complicated for most people. 2 times 2 equals 4. I think we can accept that. So divide both sides by 2. You get 2 is equal to 4 over 2. So I put 4 over 2 for that 2. And see with 2 in equation number 4? Well, I put 4 divided by 2 in equation number 5. And in equation number 5 also, we divided out the GUVs across the board. So there you got it. Equation number 5 is also necessarily true. Okay. Now, we already talked about the number 4 and how freaking amazing it is. So I even put it in equation number 5. I put it in red brackets to highlight. It's like ooh, there's a 4. There's that number 4. Geez. So we know from our previous work that 4, you can substitute G subscript UV times G superscript UV. It's the same as 4. It's equal to 4. So that means that if equation 5 is true, and it is physically true, equation 6 must be physically true. So I take that 4 and I substitute the same thing, which is G subscript UV times G superscript UV. I stick it in there, and we see that in 6. And it's like, wow. Okay. So in equation 7, it's identical to equation 6, but I put a red underline because I want to make it super clear, this last step. I put a red underline just so you look at that term, G superscript UV times G subscript UV. Do you remember that? The superscripts and the subscripts, they're both inverses in the derivatives. They cancel. So that becomes R, the scalar curvature. And we get, from going from 7 to 8, which is necessarily true, that RUV subscript UV minus 1/2 G subscript UV times the scalar curvature R is equal to K times the tensor representation of all those 16 mass densities. That is Einstein's gravitational field equation. I8 is Einstein's gravitational field equation. So I put that below there. Using Einstein's own compact notation, we arrive at his gravitational field equation, which is RU subscript UV minus 1/2 GUV R, that's what's in 8, I'm just reading it off, is equal to minus KT. Now, I took an excerpt from Einstein's book, equation number 96, and where he writes it, I think this is, maybe there's two times he actually wrote it out, and this is one of them. But I think it's only actually one time in his book where he wrote this out. And remember, this is 1954, so if he was going to change it, he would have changed it before this. And his says R subscript UV is minus 1/2 subscript UV G subscript UV times R is equal to minus K T subscript UV. Same as 8, the same as I wrote below in that yellow square. It's not equation 96. Now I want to say, this is what Einstein had to say about it. He says, further, it may be proved that the third condition requires A to have the value negative 1/2, and he's talking about this 1/2 in front of the GUV times R. And all he said was, it may be proved. It may be proved. So I try to even parse that. It, meaning the value is 1/2. So negative 1/2 may be proved. May be proved. Yes, okay. I guess that makes sense. But he didn't prove it. Well, the neat thing is this derivation I've just shown, this very simple derivation, I proved it. It's proved. So And so many times I've watched videos and they go along, they're explaining it, and it takes hours and hours. Well, I'm not so quick either, and I talk a lot. But anyway, so and then when they get to this critical part of why it's 1/2, why you have to subtract 1/2 GUVR, they say, oh, it's something to do with the conservation of energy. Of course, everything has to do with the conservation of energy. And oh, we send it away to the mathematicians. Einstein sent it away to the mathematicians. Back comes the answer. And don't ask what the question is. Just do the math. Well, you want to know? Just look at my derivation there. I've derived why it's 1/2 and why it has to be 1/2. So that's kind of exciting. We have here one of the first. I haven't seen such a complete derivation, so clear and complete. We know why it's 1/2. We know what a scalar curvature is. We know what the scalar tensor is. Well, scalar mass density is. We know what the TUV is. We know what RUV. But we don't know what K is. So let's go and let's derive that right now. So let's derive K and a few other things. So the value of K, that is. So let's see, what do I say here? Test the last result to see if it agrees with Newton's result for low mass and low velocity using Einstein's choice of the metric signature, which is, as we've said before, -1, -1, -1, -1. Okay, so Einstein's new expanded gravitational field expression has to dovetail with Newton's view when you reproduce what Newton was measuring, because Newton got the right answers for within his scope. So this to get the right answers, this gravitational field equation must produce the same answers as Newton. And we already worked out the Newton's curvature, 4 pi r squared, 4 pi r g, 4 pi g rather, 4 pi g. So when in the low mass and low speed, basically pseudo flat space situation or approximation, we have to agree with Newton. So we have to, that's how we're going to get the value of K, because we can adjust K so it agrees with Newton, and then we're home free here. So what value of K to converge with Newton at low speed and low mass? Question mark. That's the question here. So we start with what we had before, which is R is equal to KT. That's from previous page. And we take Einstein's field expression we just derived, and I write that down. I haven't derived it here. We derived it in the last page. And the reason I wrote those two is because we're going to take, notice in equation 2 we have KT. And in equation 1 we have that R, the scalar curvature, is equal to KT. We talked about that last page. Well, I can, and follow that red curvy arrow. We can take that KT and substitute R for it. And R is equal to KT. So we do that from the field equation before, which is here. RUV in the bottom there in the yellow box. RUV minus 1/2 GUVR, right? Well, in that we put KT, we stick it in there. So we get RUV subscript UV minus 1/2 G subscript UV KT. It used to be R, now it's KT. That's expression number 2. And of course, that has to equal K times TUV, which is from before as well. And we don't know K yet in this derivation. So then 3, we have that RUV. We throw it, this entire thing that's underlined, minus 1/2 times GUV subscript times KT, we throw that over to the other side of the expression. So we start with KT u subscript uv, which we already had on the left-hand side, or the right-hand side rather. We throw it over on the right-hand side. And then we pick up the negative 1/2 GUV times KT, but when it goes over from the left-hand side to the right-hand side, it reverses sign, of course, so we get plus 1/2 GUV times KT. So nothing fancy there, although, it can trip up easily. And this tells us RUV in terms of TUV, using, of course, Albert Einstein's chosen metric signature. All right. So then we go from 3 to 4, and where I don't talk about all the RUVs, I talk about one particular one. And we're looking at the low mass, low speed approximation. So when we're going to get R00, the R00, which refers to the scalar curvature for, not the scalar curvature, the tensor curvature, for the mass, the first term, T11. So T11, and we worked that out. In Newton's case, it was 4 pi times the mass density. So the curvature is equal to 4 pi, which is, we already know, is for Newton, the curvature divided by the mass density, and then you multiply the mass density. And so we put in the R00, and that's going to have to equal, from the equation above that, KT plus 1/2 GUV times T00. So we put in then that's going to be equal to negative 1/2 times K times the negative mass density. Because Einstein, his choice of metric means you got to stick in the negative mass density, because it's -1, -1, -1, -1. So it's one of the kind of strange things, but Einstein is saying that the gravitational mass is actually a negative energy. That's interesting. It's reflected in his choice of metric, a tensor. So then we go from 4 to 5, which says that 4 pi g is equal to, and I take the negative and I cancel the negative, negative 1/2 times k. You cancel out negative, and you get positive. 4 pi g times rho is equal to 1/2, positive 1/2 k times the mass density. Now, we went through this and we got the expression number 5. Now, expression 6 is actually the answer, because if you look, 4 pi g times rho is equal to 1/2 k times rho. Well, you can cancel the rho's on both sides, the blue rho symbol there, on both sides. So you get 4 pi g is equal to 1/2 k. Well, you multiply both sides of the expression 4 pi g is equal to 1/2 k, multiply by 2. The half goes away on the left-hand side, leaving just k. And on the right-hand side, you have 2 times, because I multiply by 2 on both sides, 2 times 4 pi g, and remember we canceled the rho, so 2 times 4 pi g is 8 pi g. So k is then equal to 8 pi g. That is the value of k. So we went through relatively simple substitutions of what we've derived in the previous chart, which was Einstein's field equation, made the appropriate substitutions, and we get the value of k, which 8 pi g, which allows Einstein's field equations to dovetail very, very exactly with Newton's results, where Newton is true within its scope, and so we narrowed the scope down to that scope on the Einstein's field equation. We got a perfect match, provided we use k is equal to 8 pi g. So Newton had k is equal to 4 pi g. We have to, in our expanded field equation, use k is equal to 8 pi g in order to get it to converge with Newton, so which Newton was true for its scope, to get the Einstein's general field equation to match with Newton under that reduced scope. To do that, you need k is equal to 8 pi g. We just proved that. So, lo and behold, we get this explicit Einstein's field equation, which I wrote below. R subscript uv, the tensor curvature, minus 1/2 g subscript uv, the metric tensor, times the scalar curvature r is equal to minus 8 times pi g times, which is k is 8 pi g, so it's, and Einstein's equation is minus k, so minus 8 pi g times t subscript uv. And k equal to is 8 pi g, and that comes from the small mass and low speed approximation, where that value allows Einstein's equation to merge, as it must, with Newton's results within that scope that Newton was working in. So I want to just summarize these. I put them in boxes so I can, in blue boxes here, so I can pull them out and summarize the results. Here's what we've established. And each one of these boxes is like an eye, like a perceptual organ that you can look in, and it's like an X-ray vision into Einstein's field equations, and which is basically an X-ray vision into space-time and its curvatures. So the summary results. First one. The 16 waves can propagate through the vacuum R, and I list them, the various directions, and there's 16 of them. And then we have the explicit expression, which I just talked about, R, with the 8 pi g in it, though. Einstein's gravitational field expression, right there. R minus 1/2, R subscript uv minus 1/2, g subscript uv times the scalar curvature R is equal to minus 8 pi g times the tensor version of t, which is t subscript uv. There we have it. Okay, so that's, and then we know that R, the scalar curvature, is equal to k times t, the scalar mass density. Okay, so if we want to look at each component of t, the scalar mass density is going to be equal to the component of R, the scalar curvature, on a one-to-one match, provided you do the constant of conversion there, k. Okay, so we know what R is, and we know once we know the mass densities, all of those, we know what the scalar curvatures are. One-to-one match multiplied by k. So that's like X-ray vision. We know everything there is to know about R right there. Okay, so now R subscript uv, the tensor curvature. Remember I said there's two directions in each one, so it kind of gets a little bit out of our normal, let me say, out of our normal range for our physical intuition, because we don't have so much experience with that. At least not overtly mental experience with it. But R subscript uv, and you want to know how it relates to the mass densities, both the scalar and the tensor version. So you want to know how it would match with TUV, and you find out that, oh, you actually need two things. You need to make this one-to-one match, you need a little bit of the scalar curvature T and some of the tensor curvature. There's a little bit of a mixture when you go from one to the other. This is sort of a surprise. So this box here, the R subscript UV box there, second to the last box, that's like a perceptual organ which allows you to look at, you want to know what RUV is in terms of TUV. If you want to know what the curvature, the tensor curvature, how that relates to the mass densities and vice versa. This is your perceptual organ. This box here, it says that R subscript UV is equal to minus K, and we know what that is, times the tensor version of all the mass densities, including the directions, plus 1/2 times the metric tensor G subscript UV times K again times the scalar mass density T. So I'll just read it off using the symbols here. R subscript UV is equal to negative K T with the subscript UV plus 1/2 times G with the subscript UV times K again times T. It's not quite what we would have expected, but it's true. We proved it, and it's accepted physics now. It's been that way for like 100 years. And lastly, that K is to make the match with Newton under the reduced scope of Newton. K has to be 8 pi G, so that's what we use. So there you have it. That's basically it. We know we're using these windows. We can look into every component of the Einstein's gravitational field expression, and we know what it means, and we know what the values are, and we know what's scalar and what isn't scalar, and we know what a scalar means, and what a tensor means. Basically, we know it all except for the details, some of the particular solutions to this under particular physical situations. That requires a lot more work, of course. But in terms of comprehension, we can see it all at once, right here. You see it all at once. You have the perceptual organs to perceive it, to look in any direction at anything in Einstein's gravitational field expression. So with that, I want to thank you very, very much. This has been a truly exciting voyage of adventure for me, and I hope it's been an exciting voyage of adventure for you. And when I embarked on this, I wasn't sure I was going to get to this stage because I wanted to not jip myself from the experience of struggling with it the same way Einstein did. So I didn't want to just follow everything. I wanted to put myself in Einstein's shoes and actually have to figure it out and make lots of mistakes, along the way, and learn from that and grapple with it and shed light on this. And it actually came to fruition. I feel so gratified at the results, because I can now see. I've got the vision. I can see into this. I hope we can share that. But let me just say again, thank you very much. It's been a wonderful experience, and I hope you enjoy it. Checking out now.